We are happy to be able to have here and welcome two guests from Mannheim. The first speaker will be Kirsten Marlowe, and she will speak on growing trees. Interesting topic for all of us. The second talk will be by Michael Piotrowski and will start short after 3 o'clock. So I just want to tell all who are here and have a restricted time for sitting here that definitely we will end up by 4:15. So, first speaker, please take the floor.
Yeah. Thank you very much for the invitation. I come from the Institut für Deutsche Sprache because it's for the German language. We also only have a German name. It's a Leibniz Institute. Most of my colleagues are Germanists. I'm one of the few computational linguists. I'm with the Institut für Deutsche Sprache for almost a year now, and I've been before at the IMS in Stuttgart and in Konstanz and in Basel and in Zurich, and I studied in Germany. And I have a long time interest in writing and what is happening during writing, how do people write, and what can we do as computational linguists to provide better writing tools. And in order to develop these tools, we have to know more about what is going on during writing and what can be done with the help of computational linguistics. And what I'm looking at today is incremental parsing during writing. So it deals with what's happening to the text. And I choose the title Nonlinear Incremental Parsing to make it a bit obvious what I mean by incremental parsing. However, I will first explain different notions of incremental parsing, then some specialties about writing, and then I come to the topic of growing trees. Obviously, it's parse trees. So incremental parsing is a term that is known in computer science and is also known in NLP, but with a different meaning. In computer science, it's a process that you have or you can use when you code something, when you program. So then you have incremental parsing in your programming editor. So this is an ongoing process that is running while you code. And the idea behind this is that you parse the structure of the program you have so far. And when you extend your program, you edit something, then this change structure is parsed again, and the parse tree is adapted so that your parse corresponds to what you have written in your editor. And in NLP, incremental parsing is rather a batch process, so you run it once on a text that is there, that is not under development, but you have a text and you want to parse it, and one approach to parsing is this incremental parsing, and then it's to parse a sentence word by word. So this incrementality is how the parsing is done, and not in the sense that this is done during the evolvement of your program. And if you look at writing, then this writing is, in one definition, the creation of text, and especially it's a nonlinear creation of text. Of course, it depends a bit on your own habits. Someone may be able to, even if some people are able to write a big program just in one run, and then everything is fine, no errors, no warning, nothing. And there might be authors that write a big poem or a big scientific article just in one go, linearly, but that's very rare. So usually it's nonlinear. And also, writing differs from various other modes. Writing, of course, differs from speaking. While I'm speaking, I also utter one word after the other, but I just can add another word and another word and another word. And if I started my sentence in a way that I have no chance ever to end it grammatically, then I'm lost. I'm not able to go back and change the beginning. I just can add another word. And that's similar to hearing. As a hearer, you can choose at one moment to skip listening and just skip a word, but you also hear a sentence or a text one word after the other. So your internal parsing as a human and also your parser for speech recognition has to cover one word after the other. In reading, we can go back and forth. You can read linearly, of course. You can read every word. You can skip words. You can go back. But you cannot unread a word. Once you read it, then maybe you can try to forget it, but somewhere it's there, and if you process it automatically, then it's there. But for writing, you can unwrite something. Before you give your text to your supervisor, to your publisher, you can delete things. You can delete things you have written before, and nobody know that you have written them before. So you can really undo things. And you can produce the words that make up your text in various orders, and nobody will ever know how you produced this text. But while speaking, you can follow how this evolves. So that's the challenge for analyzing or for processing writing, and that's especially challenging when you want to process this writing process just as it happens, so in a live fashion. So I said before, it's non-linear, and I can have revisions. I said I can unwrite or delete words, but I can also go back and introduce and insert other words. And I can take parts and move them around and try out how this feels, how this reads, how I like the argument when I switch positions. It also has a bit of a notion of big data. I can come back to this in a moment. In writing, more than in the other modes, I have media discontinuity. Of course, this depends on how I write and who I am and if I collaborate or not. And the writing is author dependent, and it's more so if I write collaboratively. Then the process is different than if I write on my own. And also, I have maybe a different writing process if I write in my native language, or in my first foreign language, or my second foreign language, or in a formal language, or whatever. So for the media discontinuity, I have 3 examples, snapshots, and it's not about the text at all, but just about the appearance. So it's obviously printed text here, and then someone made notes around the text. That could happen. And then the person, probably the same person, started to make drawings so where this note does belong to. And this page is an example from James Joyce, when he, from a publisher's point of view, unfortunately edited, or he it says corrected, but he reviewed the galley proofs, which are intended to just make 3 minor changes, and then we give it to the printer. So James Joyce is known to produce more than half of the final text on the galley proofs, on different stages of galley proofs. So this was printed. He made the notes with edges and arrows and numbers also. And obviously someone else had to go then and try to figure out where these things go and how to change these things again and make a nice print and send it back to James Joyce, and hopefully with only a few minor corrections. A bit younger example is from Max Frisch, and here you can see that this is probably written, this is typewriter writing, and he had at least 3 modes of revising these things. So small things he revised obviously when still using the typewriter, so he moved the carriage around and cut out these things here. He also added some words while still being on the typewriter using the carriage. Then he used the pen to cross out things. a pencil, and a pen to mark insertions. So maybe he had 3 runs to revise his text. One just while he wrote, so probably somewhere when still being in this line, but maybe he also used the scrolling function to go back to one line. Then he crossed out things and he introduced new things. And another even younger example, that's from a photograph from very far towards, that's Obama's left hand and right hand. So he had a speech, and that was in preparation when he was running to become president the first time. He had a speech. We don't know if he wrote the speech or not, but as he's going to speak it, to read it, probably these notes are in his own handwriting. So while reading it, he has to manage to see that somewhere he doesn't tell this one, but this one, and then he goes on and introduces, and so that's a very hard point too. That's not intended to be printed again, but he reads it. But he has these different media that he's dealing with it. And of course, you have these media discontinuity if you think of using speech recognition and dictation. There can happen all kind of things. You can also read these text-to-speech programs to be able to detect spelling errors, because then some funny words occur that the program might not be able to pronounce or pronounce strangely in these things. And I said we have this aspect of big data. When you write with a computer tool, with an electronic tool, you can today have these keystroke logging. So there's a software sitting on your device logging everything you do. And these keystroke logging softwares today are so lightweight that they don't slow you down. You don't realize them. There's no funny symbols popping up. And so if you know it, but after 10 minutes or so, you forget about it. You don't notice that there's something sitting. And these things log every keystroke you do. And of course, when you think about all these texts and forum posts and Facebook things and Twitter and blog posts and scientific papers, we produce a lot of written text today. So these keystroke logs are big and they grow as we type. So that's also one big data approach. If you want to process live, then you have to deal with that this is continuing and this is growing. As an example, what size this can get, and I will use this example text in the following slides too. For 23 minutes writing session, where one person produced in the end a text consisting of 160 words only. So the person had a topic and an idea, and then set themselves the goal, okay, I will produce 150 to 160 words. And they typed and deleted and inserted a lot of things. And for these 160 words in the final text, they produced 2,000 data points, so 2,000 keys pressed before they end up with these 160 words. And in this particular XML representation, it's 1.3 megabyte of XML data. And 23 minutes is not long, and 160 words is not much. That's so much text. So we produce a lot of text. And to show an example, I have the snapshot for how to produce the German determiner D at the beginning of a sentence. So that's three keystrokes, the capital D, the small I, and the small e. And as we are in the start of the text, we are at the position 0. After that, our document has a length 1, and in total we have produced 1 character. That's the system time when we started to press the key, and also the clock running for the writing session. And that's the time when I released my finger from the key. So I had my finger was 250 milliseconds on the key before I released it, and before that I paused 0 seconds. And I'm at the beginning of a word. Then I'm still on the keyboard. produce the small I at position 1. My document then has length 2. The next time, and between the D and the I had a pause time of 230 milliseconds, and I was a bit fewer time on this key than on the capital D. But I had a lot of data for just 3 letters to produce a determiner. But on the other hand, I know everything about it. The only thing missing here is some XY coordinates on my paper where exactly I'm in. So I'm just measuring the length, the position in my document. And this is also part from some example data I use here. That's a writing session from a seminar I gave a few years ago in German. So they're all German students, and they wrote in pairs and logged their keystroke activities, and they observed each other, and they came up with a research question, and then they tried to answer this question. But that was the official description for this experiment in the seminar, but I was mainly interested in the data they produced. And the setting, they wrote an argumentative essay with the text should then have 150 to 160 words, and they set themselves the restriction to only write 25 minutes to produce this small text to a free topic. And this topic here for this text is roughly, should assisted suicide be legalized or not? And the content answer to this is, it depends, of course. It's an argumentative essay. And their research hypothesis was when they set a restriction on time, these 25 minutes, and on the size of the final text, these 150 words, then this will trigger a lot of revision. So a lot of things should be going on, and in the keystroke logging, they will delete a lot of things, they will introduce a lot of things. And they looked at the data, and they could prove this only for size, so that the time restriction had no effect, but saying, okay, I have it 150 words or 160 at most, then this triggers revision. And they also moved around some noun phrases, some complex noun phrases with, I think, 3 adjectives, a determiner, 3 adjectives and a noun, and replaced it by a pronoun. And then when they saw, okay, I have some words left, they introduced this complex noun phrase again. So there was some things going on. And I logged this data with input log. Input log is a keystroke logger that's freely available from this website. It's developed in Amsterdam for some years now. It's still maintained, and there are still new versions. The only drawback is it's only running on Windows, and it logs word creation. But on the other hand, you start this keystroke logging session, so you explicitly do this, you know that you are recording yourself now, and then nothing else bothers you. So there comes this data from. The other aspect I said, in writing you have revisions, and writing is non-linear. So this means that I can have, and as revisions I say that's deletions and insertions, and also if I move things around, I delete them at one place and insert them at the other place. And I can do that at any time, at any location. Of course, I also can revise mentally, but with keystroke logging, I can only log what's going on in the paper. And there's an established notation, S notation, for marking these revisions, deletions, and insertions. And that's a snapshot from the starting of the text. The pipe is a break in typing. The numbers are the indices, and it's growing through the process. Everything in square brackets is deleted, and everything in curly brackets is inserted at a later point. So from the very beginning, you see typing, then the H is typed, and immediately after that, the person realizes that this is a typo, deletes the H, and produces a G to make it a proper German noun. Then writes again, and you see here the interesting thing here is, and that's the effect of the size restriction, that in the beginning it's the indices grow, but then you have after the 2, you have a 67, 68, 69. So at a very later stage, she came back to the beginning of the sentence, of the text, and deleted things and inserted things. So you have a mixture of smaller and bigger indices. When you see the effect of other typos, and the Ö and the A are neighbor keys on the keyboard, so maybe it's a mismatch in fingers. Sometimes the letter is deleted and corrected immediately. Sometimes a longer sequence of strings of characters is typed, and then she realizes it and deletes everything just to, in the end, replace the Ö by the Ä. So there are different approaches to how to correct typos. When we want to process this data, we can say, okay, we have to define certain points when we run whatever process. And the text under development has various states, and it depends on your definition what a state is, how many states you have. And the very low level one is a state of the text is whenever I press the key. That's a new state. And I have, for the small text, I have these 2,000 states. Or I can say whenever automatically or manually something is saved, that's a state. So, and this, for this text, Word saved after 2 minutes automatically, and then the last version is saved by the writer manually. So I have 3 states. Or I can say every time I revise something, either I delete something or I insert something, that's a version. Then I have 97, and that's 97, it's the highest index in my S notation. I can have access to this immediately. Or I say one particular state is a change in production mode, and I come back to this in a minute. So I say, okay, a state is a version of a text. And then I can say, okay, I want to apply NLP methods, various, to particular versions, and thus to the growing of the text. I could have information on the current word my cursor is on, or I just have written. I could show information on the current sentence. And if I can do this, then I would be probably interested in differences in diffs of these versions. So what is going on between different versions? And I want to visualize this. By visualizing these diffs, I visualize the growing of the text, except from following a replay which letters appear on my screen. And a change in production mode I define as a switch from normal text production to either deletion or insertion, or from deletion to insertion or normal text production, or insertion to deletion or normal text production. So I have 3 production modes: normal text production, deletion, or insertion. And normal text production is typing at the edge of the text produced so far, so at the end of everything I have written so far. Whenever I move my cursor to another point in the text, then obviously I have a change in production mode, and I then will either delete something or insert something. And this definition allows implementation, of course, because I can operationalize version as a state where I can use the very trivial undo command in editors. Whatever I can undo, then I arrive at the previous version. So I can actually implement these notion of version. And if you look at our example text and these explicit versions, then I have these that's the 7 first versions. The person typed the determiner, then tried to type a noun with a spelling error in the suffix for nominalization, realized that this was an error, deleted the H, then wrote, and we are still here in the, that's not insertion, but normal text production, because we are at the end of the text produced so far. So she writes the G and starts writing an adjective with a typo again, realizes this, deletes this adjective, and then goes on, not by just correcting this this typo, but also in the same time deciding, no, I don't want I want a definite noun phrase, not an undefinite. So she used the article, then the correctly type adjective, the noun, the verb, and so on, and then types the sentence with arriving at another noun, then realizing, okay, that's a noun that should be capitalized. She deletes the whole noun, then goes on and writes still. And this is a lot of text or a lot of data compared to the same information in S notation. We also have the same thing, the typing, the deletion of the H, the G, then this adjective that is deleted immediately, and so on. So I can decide if I use this representation or this explicit representation of these versions, but it's the same information. And when I now want to show this, how this is growing, I have to find another representation of just showing this. I want something interactive, and I want some more information. I want some linguistic information, what is going on there. So there is, of course, versioning and diffing algorithms in computer science and document engineering. So I could use these diffings. However, diffing and versioning in document engineering is using explicit structures of documents. So they are using the XML structures, the TI structures. They are looking on these. And they focus on the document, not on the text and not on the linguistic structures. Of course, we have NLP parsers, so we should rather use those. And then, of course, natural language text has structure, but that's rather implicit. The syntactic structure is not visible somehow. It's in there, but you have to run a parser to make it explicit. You have these rules. You know how a grammatical sentence should look like, but it's not explicit. It's not tagged when you type it. But you can make it explicit. But when you write, it's implicit. You have to use parsing to make this explicit. And moreover, and that's the same, of course, in programming, during writing, your sentences are ill-formed, incomplete, inconsistent, whenever you decide to revise something. So when I say a state is when I decide to revise something, then I might be in the middle of a sentence or even in the middle of a word, and that's not grammatical, not valid. So the big question is, when do I parse? And how do I diff these parse trees? Of course, there's diffing in parse trees when you run several parsers on one and the same sentence. Then you can compare these parse trees. But what I want here is a slightly changed sentence and the diff of these parse trees from the first and the second sentence. So the sentence changes. And probably we need interactive parsing. So this has to go fast, and I want to send something and get it back in immediately. So I want to somehow automatic reparsing to have this incremental parsing from computer science. To be a bit careful about space and running time, I would like to avoid reparsing of untouched sentences, because if I did not change anything there, the parse tree would be the same. So there's no sense in reparse this again. I also would like to avoid constant reparsing at specific times. So I could say I parse after each key pressed or after every second, and that's probably too much. And that's also too heavy to the machine. And as I told you before, this person played around with a complex noun phrase and the replacement by a pronoun. And she really had this complex noun phrase in the buffer and inserted it and deleted it. So she could do this with 1 or 2 clicks. And of course, if I have this noun phrase parsed, I would like to just take this subtree and reintroduce it. There's no sense to reparse it again and again. So I want to parse during writing. I could say, okay, I parse every time when a version is saved, either manually or automatically, and I only parse the sentences where something has changed, only sentences I touched after the last version. Or I could say, using my definition of version, that I say a version is defined by a change in production mode. Every time I have a change in production mode, I parse again the touched sentence, only things that have changed. Or I parse the current sentence my cursor is in at the moment after a change in production mode. So here I say only the current sentence, and here I say the touched sentence or sentences. Or I say I pass everything after a change in production mode, everything I have at this moment. And that's what I'm doing now, because that's the easiest one, right? I don't have to care about sentence boundaries and current sentence and touched sentence or untouched sentence. So at the moment I pass everything after the change in production mode. It's easy to find the change in production mode because my cursor moves somewhere else. And then I pass everything. But that's not the very best idea. What I will show you, a few things. I use Emacs as a test bed because it's not input log. What I'm using here is for logging, but it's easy to log. I have access to everything. I can define what's the current word, what's the current line, what's the current sentence. And what is available is information on the current word. And the current word is the word my cursor is on at the moment. And for this I use, they have funny names. The morphological analyzer is called Stripy Zebra. Don't ask me about the reason. It's implemented in Malaga, and Malaga is a framework for left associative grammar for German morphology. To my knowledge, it's the most sophisticated parser in terms of output, but it has a license and is no longer available, but I have one. But of course you can plug in SMOR or every other available via license or free morphology. Then of course it's possible to, and one reason also is that Malaga is able to run things interactively. And of course I can have information on part of speech structures, and this leads then to an actual syntax highlighting in comparison to in programming. I don't have syntax highlighting there, I have keyword highlighting. But with the part of speech tagger, I could actually highlight syntax structures. Of course, it depends on the quality of my part of speech tagger. And here I use MBT. That's the tagger, the memory-based tagger from now Radboud, formerly Tilburg. And it's trained with the same data you would train tree tagger for. So but tree tagger is not cannot be used interactively. It has never been intended to be used interactively, but MBT can be used interactively. So that's the reason there. And then I have information on syntax structure of the current version, so everything I have typed so far. And I use here also just out of the box the made parser for German. And for the for the morphological analysis, it again is the, I don't know the number of this version, but some stayed in the production, and you can just this this noun, you can analyze it morphologically, and then get very structured information that this is a feminine noun, a singular, composed of a stem of a verb, and then the suffix ending to make it a noun, and also other things where I can see that this word where my cursor is currently on is an adverb, a modal adverb, a positive form. It's stored as such in the lexicon, and it's here used as an adjective. I can have this information, so I can point on a word and get this information. There's obviously no real reason to show this information for every word I'm just typing. That would be a bit too much information, and of course I can filter this information and just show part of speech or whatever. And I can also have, as I said, okay, that's funny. The pink ones are verbs, finite verbs. You can't read the letters anymore, but this is correctly tagged. This is the ist, so the form from to be. But this is actually an adjective, so this is wrong. This is correctly. This is also correctly, and this is an infinitive form. Yeah, and some are. Yeah, and this also should be tagged, but isn't. But that's due to the quality of just running MBT with an ordinary training file and on this data. I have another text where it's a bit better. I mean, you can say the first text was produced by a student, and that's from a journalist. That's just from a newspaper, and here it's a bit better. So it's durfte, wird, beherrschte. Während is wrong again, but also you have this effect. Where is it? With the German particle verbs, where the particle is sitting at the end of a sentence, and this is covered as well by kündigte an, so this is covered as well. Another one is to recognize, wahrnehmen, nahm, wahr, and you could think of if I decide to change the verb from recognize to see, then what I usually, or what a writer usually does, is say, okay, so it's past tense. I take sah, the form from see, and the particle is still waiting over there. But that's what usually happens when people revise text and make changes from verbs with particles to verbs without particles, or vice versa. Usually the not so interesting part, the particle, is still sitting somewhere. And with this highlighting, of course, you would see, okay, there is still something that I should have get rid of this one too. So there might be a better use for actually having this running during writing. And I don't know if you see the advertisement for the editor AI writer. They advertise that they now have live syntax highlighting. So as you type, some words were green and some red, and so the adjectives and the verbs are highlighted in this way. I don't know if they read our paper before or not. And I made I prepared something for the syntax structure. So if I use the same process of typing this text. So when the student arrives at this stage, and then she realizes that there's a typo here, I should do something. So this is a version, and then the parser fires and outputs the parse in the Connell format. And because of the typo here, of course, it's not recognized as noun, but guessed as a named entity. Then she deletes the H. The guessing doesn't get better. But when she correctly types the G, then this is correctly recognized as a noun. And the adjective with the typo is again not recognized, but represented here as something else. She deletes this again, so I get back at the article and the noun. And then she writes further, still this is in only one sentence. Everything looks correct except of the noun with a wrongly small, with a lower T, which should be a capital T. And this has the effect that there is also an error here. And when she deletes this, then you see that this is correctly parsed, and then again here we have an unfinished sentence, and somehow this doesn't make sense. But what we can see here is between this version and this version, I end a sentence and start a new one. So when I say parse only the current sentence, that would be too few. That would be only the last part. If I say all touched sentences, I would get the same parse as here, because my text is so short at this point. What is a bit a question, is this parse readable to a normal writer? Does this make sense? Does this give you any information? Except, I mean, you can see here now that this probably is well formed and everything is okay and it looks nice. So I come back to this later too. What I try to show here is the nonlinear incremental parsing as parsing of text during production. So I would say there is a value, and we should do this to parse the text before it's finished. It's especially valuable for linguists looking at how people use language. If you are looking how do syntactical structures evolve? How do they change? How does punctuation change? Then there's no sense in looking at published newspaper articles, because there is a corrector between the author and the publisher. And of course, this corrector does know the rules by heart, and she or he will remove all the wrong punctuation marks. But the writer might have used them. So I have a colleague who is interested in looking at why there's a strange phenomenon in German of the Vorfeld comma. So there's a comma that looks like you would use it in English, but it's not allowed. It's not usual. It's not allowed in German, but people do it. But you cannot find them when looking at newspapers, because these correctors remove them. If you would have access to what people do during writing, and I catch myself that after she told me about her project, I do that all the time, of course, then you would be able to see that people either use it or not, and then you would have the chance to talk to this writer who used it, why she first introduced it and then maybe removed it or not. So there's no other access to these things. So I would argue for applying these computational science style of incremental parsing that is happening during programming when you code natural language text. But we need different tools and different approaches for this kind of parsing. We have interactive NLP tools that can where I can send something and get the result back very fast, but these are still meant for static use on word and on sentence level in various languages. And the open challenges, of course, are then how we display these parse trees to a writer so he can make use of it. Of course, the Connell format is a format that is very nice in terms of space, but maybe a normal writer would be more okay with a traditional parse tree with leaves and edges and things. And then if we can find a way to diff these parse trees, which is a task in itself, then how to display this diff? I can display another parse, but the writer should see what is different from this to the other one. what changed there, either in blinking or coloring or graying out things or whatever, maybe even customizable. And then if we think a step further, it wasn't such a good idea, structured programming in the 80s, but a bit of it we still have. If I can parse the document I have, and if I can make this outline, the structure visible, then maybe I can rearrange parts of my document by just taking a structure element and moving that around, and moving it one level higher or up or whatever. So maybe I would also like to grab a subtree and move that around. Or I mark two trees and say merge. Or I mark a sentence and say passivize, please. So I operate on the parse tree, but it has an effect on the text, and I don't have to do it in the text and then still have my particle waiting over there. And another application, and this bit relates to the talk by Michael, when we have this notion of a version, what's differences between versions, and I showed you these media breaks in producing text before. These are, of course, data from Joyce and Frisch are used for making scholarly editions of how an opus is produced and how many versions there were and when did he revise which one and which secretary lost which page and so on. So maybe we could use this definition also for scholarly editions and make these digital editions a bit more accessible and a bit more interactive for users, and also include the linguistic information on these things, and not only the content and the wording and the writing style and fonts and these things. I didn't look at the watch, but I'm done. I mean, I have this starting of the I used this example with all these 140 versions and said, okay, I need a parse for every version I have. So I have these 140 parses. And I only showed the Connell parse here. I also had a colleague parse every version with an LFG parser, but this gives, of course, huge trees for every sentence. This is even more not so useful in an editor, maybe then with a different window where you have even more information. And at the moment, I'm also not bound to a particular parser or particular or if it is dependence or phrase structure. In the end, the user should be the main factor to decide what is more useful when I write, and it's probably also different if I'm an experienced writer, if I'm a journalist, or if I'm a fifth grader, or if I write in my native language or in a foreign language. Maybe it's even maybe most important for the fifth grader writing in a foreign language, who heard about syntax before, who can make use of things, or could then combine this when translating things. So the target syntax tree and the source syntax tree and these kind of things.
I would just elaborate on the question by Martin. Well, the story is that now we know that you use LFG, but the real story is that you are parsing things which are, so to say, very often unparsable because they are not grammatical. And so now I feel that the question was, how do you cope with this kind of problem? Because you have hidden away from us all the structures and all the process of parsing. And this is exactly the most, at least for the two of us, the most interesting part of the So how do you parse sentences which are unsentences?
I mean, there you have the same problem that you have for grammar checkers. You cannot, either you have a robust parser, then you will get a parse tree whatever your sentence looks like. So it corrects things on the fly. Or you get with LFG, for these non-finished sentences, you get only parse fragments. And the big question is, maybe this is still useful for the user. So there's a huge aspect of interfaces, of human-computer interaction. Of course, MATE always produces a parse. But the LFG parser for most of the sentence only produces fragments, making it obvious that there's something that the writer probably still has to do. But of course, parsers are designed to be robust, to be able to parse all this Twitter and blogging language where you have ungrammatical but published text. So this robustness is a factor that you, for these purposes, either have to interpret in a different way and make this obvious that there's something happened in the output that the writer has to fix on the surface, or you have to get rid of this robustness and say, okay, that's not finished, but maybe you will finish the sentence.
I wonder if you make the difference between a partial parse and something that is most likely wrong. Like, I mean, if you have a subject and a transitive verb, but the structure is lacking the object, so you only get a partial structure. That's one case, and the other case would be when the agreement is wrong between the subject and the verb, no matter whether it's transitive or intransitive. Yeah. So is there a difference in your system in how you tackle these two cases?
I mean, you would also get fragment trees or subtrees, and then I also made experiment with published text, which have these grammatical errors, and the out of the box, the state of the art grammar checkers do not find any error. But when you parse it with MATE or with LFG, you get these. With LFG, you get these fragmented parse trees, indicating that there is something wrong with this sentence. And then, of course, you can use this information to be able to fix it. And then the writer has to decide, oh no, this is an elliptical sentence, I want to have it this way, because it's for literal, formal style reasons, whatever, or this is actually an error and I do something about this. So this is really in reaction of the one who's looking at this parse tree to be able to see that there is something, let's say, unusual. Maybe it's an error or not.
Okay, thank you.
Just as a help that you can see the parse trees as you type, or will you highlight the errors somehow? Or
I mean, this is really explorative research. So, and where I'm coming from to this point is really that I looked, and when you start reading these things, you see it everywhere. These ungrammatical sentences, agreement errors, word order errors, missing verbs, missing words, duplicate words, and these are not detectable by grammar checkers. So your editor your word processor won't help you. Someone has to read it. And maybe one effect is that most of those errors are really introduced when people revise their text, when they play around with, and in languages like Czech and in German, you can play around with word order. And at some point you get a mess. And if you are able to detect the point in the revision process where something goes wrong, then you might either detect the error at the end, or in the revision say, wait, you are touching also, you're not only replacing one word by the other, but you are also detaching agreement.
Yeah,
Please take care of both. You are about to replace a verb, but be aware there's a particle over there. Decide what to do about it. And most of these errors I collected, and I will release this collection with annotation for LREC. Almost none of these errors are detected by state-of-the-art grammar checkers. So there's no way that the machine can help you with this. When you read it a few days later, then you might realize this, and most of the errors are introduced because people merge sentences, split sentences, move things around, replace something, a noun phrase by a pronoun, change it from definite to indefinite, and then you have to take care of adjectives and so on. And if you're changing a well-formed sentence into something else, then there should be something telling you that you are not only make changes on a stylistic level and on a lexical level, but that you are also doing something to the syntax.
Okay, this is kind of a motivation for the research, but you have no definite plans to apply it for error checking, or
in the end it should be. There's probably not much sense, other for curiosity, to see the syntax tree growing while you type. Maybe for language learners, maybe for translation, maybe specific purposes. Mm-hmm. But for this kind of when I can detect that I'm in a revision mode because I go back in the sentence, and then I check during these revisions if I'm doing something to the syntax structure that is changing the formally well-formed sentence into a non-well-formed sentence, then something should make me aware that I'm doing something else than stylistic things.
Okay, thank you.
Well, yeah.
I have another type of question. Can you type for me? Can you say me a typical word order error in German? Some typical word order examples of some typical word orders.
No, that's not my machine. One thing you find is that you have a lot of languages for complex noun phrases, article, adjective, one or more, noun. But I have several examples of adjective, determiner, noun. And that might be due to inserting the article at a later stage, and then something happened to my mouse possibilities. Edited errors. The experiments I did, I thought that I maybe catch the students making those errors, but everything that was wrong in those texts they wrote in the first place, so they were convinced that this is wrong. But I also have data from my own writing where I merge sentences, or I split sentences, and then one of these sentences don't have a finite verb anymore, because I can omit it in a large sentence, and if I split it, I have to have another finite verb somewhere, something. And this is something I could make the user aware of, that the things that the second part or the first part that I split from a longer sentence, that this thing has no finite verb, and I should somewhere either duplicate the other one or introduce a new one. Or if I merge or split sentences, then I have the main clause and the relative clause, and in the relative clause, the finite verb is at the very end. If I change that into a main clause, the verb has to move. But if my main focus is this is not a relative clause anymore, I do the point and make it capitalized, and I'm done. I forget about the verb and it's still waiting over there. When I have a lot of missing words and duplicate words, either right after the other or a few words in between, and then it comes again.
Okay. So, if there are no further questions, I think we now have time for a coffee break or tea break or whatever. If people who have no room here want to have a cup of coffee or tea, then you are invited to my office. And we will be back after 3 o'clock. I mean, very close to 3 to listen to the second talk in this series, namely Michael. Okay? So, once more, thank you very much.